Hey everyone, and welcome to the second video of lecture 6. And this is the first of the videos where we'll be going group by group through the P block, looking at the compounds within each group. So this time we're going to focus on group 13. The group 13 I've got highlighted here. It's called the boron family because boron's at the top of it. It's got the general electronic structure of Ns2, Np2. So I can't get the lace pen up, there we go. And it consists of boron, aluminium, gallium, indium and thallium. So the maximum oxidation state is +3, and this is important for boron and aluminium. And you remember that group 13 is one of the ones where the inert pair effect dictates a lot of the chemistry, so it's 13, 14 and 15. And that means that the maximum oxidation state, which is +3, is more stable at the top. But as we go down, if you look at indium and thallium, the +1 oxidation state is more stable. And this is because the bond enthalpies are lower, so that sp3 hybridization isn't so possible. And the 2s electrons just stay, they don't interact in the bonding, they are the inert pair. So through this video, we're mainly going to focus on the top two elements, boron and aluminium. And this is because, they have more chemistry, they do more things, and we come across them more in everyday life. So the bonding in general is dictated by the fact that there are 3 valence electrons, and they commonly, although we'll see a few examples where it's not right, form 3 covalent bonds. So these compounds only have 6 valence electrons, therefore they're electron deficient, and they have 1 empty p orbital that can act as a Lewis base. And we can see here an example of BF3 and the empty p orbital, and an example of a Lewis acid Lewis base adduct. And we've touched on this before when we were looking at the boranes, which was exactly the same as this. It was BH3 instead of BF3, and one of the questions actually was how it interacted with pyridine, which is a Lewis base much like this ether is. And exactly the same thing happened. It has an empty p orbital, and the lone pairs on oxygen or nitrogen or halogen can coordinate into this empty p orbital. And as I said in that the halogens video, a Lewis acid is just something that can accept an electron pair. Now they overcome this lack of valence electrons through forming these 3-center bonds. So this is actually taken from that from the boranes, from the halogen lecture we were talking about. So this middle one is not your conventional covalent bond. It's got 3 centers, so 2 borons and a hydrogen, and they share 2 electrons. And if you need a refresher on how this works, that's in the hydrogen lectures. So they can also form dimers and polymers containing bridging groups. So a good example of this, I'll try and draw where there's space, is aluminium chloride. So instead of being AlCl3, like this is BF3, instead of being AlCl3, it's actually Al2Cl6. And this has quite similar bonding to what we saw with beryllium chloride in group 2. So you'll have aluminium with 3 chlorines. Where should I draw them up? Here. And then another aluminium with 3 chlorines. And the lone pairs on these chlorines can form dative bonds to this empty p orbital on the aluminium. So then that's where we get these dimers and sometimes polymers containing bridging groups. It's again these dative bonds, so very much like we saw with beryllium chloride in the S block lectures. So the oxides of group 13, boron forms a wide range of them containing BO bonds. The simplest is B2O3, which is acidic, and it slowly reacts with water to form boric acid. Boric acid is a pesticide. It can be used to kill cockroaches, ants, things like this. And this is because it poisons them by reacting with water. So BO bonds are strong, and they can form a wide variety of structures. and anions containing these BO bonds are called borates. So as I said, they can be a wide variety of structures. There's 6 examples down here, and they can include cyclic and linear polymers, and they contain a mix of planar and or tetrahedral BO3 and BO4 units respectively, and these are linked together by bridging oxygen atoms. And so we've got an example on the top here of the trigonal boron atoms. So these will be planar with 180 degrees between 120 degrees between each of these bonds. And as they build up, you can get these rings, and they can become very large. The tetrahedral units actually have a negative charge on the boron as well, and they can make these larger 3D cages almost, and then you can get the big polymer chains like this. And they're used in a wide variety of things. We've already seen pesticides, but insulation, ceramics, and aluminium oxide is also used quite a lot in ceramics as well. So to wrap up the group 13 oxides, let's come back to boric acid, which I touched upon a couple of slides ago. The simplest boron oxide, B2O5, reacts with water to form boric acid. But boric acid is actually quite unique in that its acidity is not due to the loss of a proton from an OH bond. So let's see how it does it. So it's none of these hydrogens from the OH groups are being lost, which is quite unique, as I said. What happens is that this boron is again electron deficient. As we've seen, it's got 6 valence electrons around it, and it's got this empty p orbital. And so what happens is it acts as a Lewis acid and interacts with the lone pairs on a water to have a water coordinated to it in this Lewis acid base adduct. And then one of the hydrogens from the coordinated water actually leaves as H+, and this is what gives causes the acidity. This is where the acidic H+ comes from. And then one more quick note about aluminium. We won't talk about it much because its oxides are nowhere near as interesting as boron, but it's forming alumina, so Al2O3. And this is amphoteric, so it can react with both acids and bases. And again, this is used in ceramics. It's also used a lot in catalysis, so I actually used it as what we call a catalyst support for my entire PhD. Let's move on to look at the halides now. So we'll start with the boron halides again, and we'll focus mainly on the boron because again it's got more of the interesting chemistry. So the first two, the boron fluoride and chloride, they're gases under standard conditions. The bromide is a liquid, and iodide is a solid. All of these have trigonal planar structures, which we've seen before. So they've got sp2 hybridization, and we saw a few slides ago BF3, and that means it's got this empty pz orbital that can take in electrons and act as a Lewis acid. So all of these act as Lewis acids, and they'll form adducts with Lewis bases. However, as we go down the group, they become more acidic, so they're more likely to interact with a Lewis base and accept that electron pair. So is this expected? Well, let's look at why this trend occurs, which is more important. Now, the reason for this is all because of two things actually. The first is the geometry around the boron atom, and the second is p-pi bonding, and they're related to each other, and we'll take it one step at a time. So the first one, the geometry around the boron atom. We've seen that in a boron halide, there's a planar sp2 hybridized structure. So we've got BF3 up here, it's planar. All of these are the 3 sp2 hybridized orbitals, and one empty p orbital that can accept electron density from a Lewis base. Now, when this happens, if a Lewis base comes along and wants to put its lone pair in this empty p orbital, this empty p orbital also hybridizes, and then we've got 4 sp3 hybridized orbitals, and we know the shape of that is tetrahedral. Now, why is this important for the Lewis acidity? Well, this changes what's called p-pi bonding. So that's illustrated in a diagram down here. So as well as the lone pair from a Lewis base being able to donate electron density into this empty 2p orbital, the halogens all have their own lone pairs, and one of these lone pairs is going to be in a p orbital that's in the right orientation to interact with the empty p orbital on the boron. So let's draw it on this top example here. So this fluorine here, or well, all of them in fact, will have a lone pair in a p orbital like this that can interact with the empty one on the boron. So they will put electron density in, and as is shown down here as well. And this stabilizes the trigonal planar geometry, because if you imagine, if we make the boron atom tetrahedral with sp3 hybridization, these lone pairs will no longer be in the right orientation to donate to this empty p orbital, so we'll lose that p pi bonding. So yeah, it's really they're stabilizing this non sp3 hybridized state. So as we go down the halogens, they get larger. Now this p pi bonding is very distance sensitive. So the larger the halogen, sort of a bromine for example, and iodine here, the bigger the distance between its lone pair in the p orbital and the empty p orbital of bromine. So that means that this p pi bonding isn't as strong. The stabilizing force of this trigonal planar geometry isn't as strong, and therefore it's easier for something else like a Lewis base to come along and rehybridize it to sp3 and make it tetrahedral. And that's why the Lewis acidity increases going down the group. Now p pi bonding is and this whole Lewis acidity is quite tricky to understand, I realise. So there's a help sheet of that on Blackboard already as well. Finally, the boron halides don't dimerize. This is again due to p pi bonding, and this would be lost if we had the B2X6 dimers. However, as I showed in one of the very early slides actually, aluminium, with the exception of the fluoride, does form dimers. So Al2Cl6 is something I showed earlier, and that has two of the dative bonds. So AlF3 is ionic and is not in dimers. It just has a large ionic structure, which is shown here, and then the rest of them are covalent and they form dimers such as the Al2Cl6.